Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology. So I also took my Bachelor's of Science at this institution as well in the Pharmaceutical Chemistry program. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so question 1 asks, how can ppm be calculated? Okay, so ppm is the short version for parts per million. So the term ppm is typically used if there is a small quantity of compound compared to the overall mixture's mass. So there are some like instrumental analytical devices that can detect very small concentrations of certain elements up to the ppm range. So they can detect very small amounts of, let's say, like trace metals or like small amounts of pesticides in like water or like in wastewater. So this is when you would use the term ppm. So to calculate for ppm, if we have the quantity of the substance, we divide this by the quantity of the entire mixture. And then we multiply this whole thing by 1,000,000. So I'm going to write it in scientific notation, which is 1 times 10 to the power of 6. So that's how you know that something would be very small in order to use the ppm concentration. Because when you have the quantity of a substance and then you divide it by the quantity of the mixture, and even though you multiply by like 1,000,000, you still get values that are around like 6 or like 10. So you know that there is only a small amount of that compound in the overall mixture. So the junior tutor said that parts per million is a unit of concentration used in chemistry. This is used to describe the concentration of a substance to a mixture of substances. Most of the time, this unit of measurement is used if the substance has a small quantity compared to the overall mass of the mixture. The ppm measurement can be calculated using the equation quantity of substance divided by quantity of mixture times 1 times 10 to the 6. You can see that the ratio of the quantity of the substance to the quantity of the mixture is multiplied to a magnitude of 1,000,000, hence the name parts per million. The quantity may vary from mass to volume of the substance, and many more types of measurement used to measure the quantity of a substance. Like similarly, there's also ppb, which is parts per billion. So this is even smaller of concentrations, can be described using parts per billion as well. So this solution is correct. Okay, so on to question 2. Write the corresponding electron configuration for the following pictorial representation. Give the full electron configuration. So in other words, do not use the noble gas abbreviation. Name the element assuming that the configuration describes a neutral atom. Okay, so they want us to write the corresponding electron configuration. So let me write down the steps on how to do so. So typically you need to write the electron configuration of, let's say like a ground state atom. So the first step in doing so is to divide your periodic table into sections for the different orbitals, which are S, P, D, and F. So I'm going to search what this will look like on Google. Okay, and you should get something that looks like this. So the light blue section corresponds to the S orbital along with helium. And this green rectangle is the P orbital. And then the middle transition metals is the D orbital. And then the last 2 rows, so the lactanides and actinides, would be your F orbitals. So this is pretty easy to divide. So sometimes you're just given a periodic table on your like test or like a quiz. So make sure you know how to divide the periodic table into these sections. Okay, so after you do that, when you start from hydrogen, you move left to right across the periodic table. And then you write your row number followed by the block letter. And then once you get to the D orbital, you write the row number -1. And for the F, you write the row number -2. So that's just like a basic, those are the basic steps on writing electron configuration. There are some instances where you need to change the order a bit, or you need to add electrons in the D orbital as opposed to the S orbital. But these are just like kind of the basic steps. So if we look at our question, they showed the different electrons that are in each of these orbitals. So for the question, in the 1s orbital, there are 2 electrons. So to write its electron configuration, it is just 1s2, followed by 2s2, followed by 2p1. So this is the electron configuration. And now the question wants us to name the element. So we kind of have to work backwards and find out what element that is. So if we go back to the periodic table and we start from hydrogen and move left to right across it, this hydrogen and the helium corresponds to 1s2, lithium beryllium is 2s2, and then finally 2p1 corresponds to the element boron. So I'm going to write that the element is boron. And this is assuming that the configuration describes a neutral atom. So sometimes you're given a question where they want you to write the electron configuration of like an ion. So they either subtracted or added some electrons. So that's when you would take that into account when finding the electron configuration of certain ions. But in this case, since boron is just neutral, it just has that given electron configuration. And the junior tutor said that the electron configuration can be written by counting the number of electrons, which are shown as the arrows in each orbital, 1s, 2s, and 2p. Thus, the full electron configuration is 1s2, 2s2, 2p1. We know that the number of electrons in this atom is 5, which is equal to the atomic number. If it is a neutral atom, then the corresponding element will be boron. Yep, so this solution is correct. I'm just going to add, since the number of electrons in this neutral atom is 5, then 5 is equal to the number of protons Therefore, the answer is boron. Okay, so on to question number 3. Label each proton with the predicted splitting pattern it would exhibit in a 1 HNMR spectrum, either a singlet, doublet, triplet, quartet, or multiplet. They can be used once, more than once, or none. Okay, so I'll just write first one of the main rules for determining the splitting pattern. And this can be described as n plus 1. So n is the neighboring atoms containing hydrogen. Okay, so this will make more sense once we start getting into the example that is given. Okay, so let me just write this out a little more clearly. We start off with a carbon that has 2 chlorines and 1 hydrogen. We have another carbon that contains 2 hydrogens. This is bonded to an oxygen group, another carbon with a carboxyl functionality, and then lastly, a carbon that has 3 hydrogens. Okay, so I'll just also add that when we have an H NMR signal, there is a signal for every unique hydrogen in the compound. So that means that every signal corresponds to a hydrogen, and each signal will also split a certain way using our splitting pattern, which is n+1. So let's start off with the hydrogens here. So when I mentioned that each NMR signal corresponds to every unique hydrogen, this means that when your hydrogens are in the same environment, then they will only show that one signal. So an example of this would be these 3 hydrogens here, which I'll just kind of box. So this is an example of 3 hydrogens that are in the same environment. They are all bonded to a carbon that's bonded to a double bonded oxygen. So if we look at these 3 hydrogens, their neighbor is the carbon that has the double bond with oxygen. So I'm just going to write that their neighbor has no hydrogens. So if we look at our splitting pattern rule, where the neighboring atom containing hydrogen doesn't have any neighbors, it is equal to 0 plus 1. So this means that this splits as a singlet. Okay, so that is for those hydrogens. Next, let's look at the 2 hydrogens here. So these 2 hydrogens are considered identical, so they also have a signal on the HNMR spectrum. And let's look at its neighbors. Their carbon is bonded to an oxygen, and it's also bonded to a carbon that contains 1 hydrogen. So this neighbor contains 1 hydrogen. So using the splitting pattern rule, it's going to be 1 plus 1, which is equal to 2. So these split as a doublet. And then lastly, let's look at our last hydrogen, which is by itself. It is bonded to a carbon that's bonded to another carbon with 2 hydrogens. So the number of neighbors, well, that carbon that has 2 hydrogens, I don't know how to word it, but yeah, it has 2 hydrogens on its neighbor. So therefore the splitting pattern is 2 plus 2, or 2 plus 1, sorry, which is equal to 3. So this signal will split as a triplet. Okay, so again, like HNMR splitting patterns can be kind of like confusing if you're not used to doing this sort of work, but once you kind of break it down and try to look at each individual portion of like such a large molecule, you kind of get the hang of the different splitting patterns that uh, that takes place in the signals. Let's see what the junior tutor said. On the rightmost part of the diagram, its neighbor doesn't have any attached protons on it, so the hydrogen atoms here can be safely defined that it has a singlet splitting pattern. On the rightmost part of the chemical structure, it has a neighbor. I think they mean the left part. It has a neighbor with 2 protons present. The rules for identifying its splitting pattern can be used where n plus 1. The neighbor atom has 2 hydrogens into it. Thus n plus 1 is equal to 3. Therefore, it has a splitting pattern of triplet. Finally, the carbon atom with the 2 hydrogen atoms has a neighbor, which is the rightmost, I think they again mean the leftmost element, with 1 attached proton into it. Using the rule, the splitting pattern can be predicted to be 1 plus 1, which is 2, which is a doublet. Yep, so I'm going to say that this solution is correct. I'll try to fix that typo, which I... The leftmost part of the structure containing 1 hydrogen will split as a triplet. Okay, so question number 4. Why is NH3 a Lewis base and BCl3 a Lewis acid? Okay, so I'll write the definition for both Lewis acid and Lewis base. A Lewis acid is considered an electron pair acceptor, and a Lewis base is the opposite, and it's described as an electron pair donor. Okay, so first let's look at NH3. It is a nitrogen that is bonded to 3 hydrogens and contains a lone pair. So this lone pair can donate electrons. Therefore, this is a Lewis acid. Now let's look at the boron trichlorine chloride. So boron is attached to 3 chlorine groups. And notice that the boron has an empty orbital. So you can see that it doesn't satisfy the octet rule. So it can easily accept a pair of electrons. So therefore, this is a Lewis base. Okay, so let's see what the junior tutor said. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. Based on the Lewis structure of ammonia, NH3, it has a formal lone pair of electrons on the nitrogen atom. This Lewis base can donate to a Lewis acids. I think they mean this Lewis acid can donate to Lewis bases. And then on the other hand, the boron atom and boron trichloride is deficient of a pair of electrons. Therefore, it is an acceptor, which is a Lewis acid. Oh yeah, so I got the two mixed up here. Yeah, so the lone pair can donate electrons, so this makes the NH3 a Lewis base. And the BCl3 has an empty orbital, so it can accept an electron pair, which makes it a Lewis acid. Okay, so sorry about that. It got kind of confused. But the junior tutor is correct. Okay, so question number 5. Sodium bicarbonate reacts with acetic acid and causes a chemical reaction. The end products of this reaction are water and what other compound? Okay, so let's write down the chemical reaction that takes place. So we have sodium bicarbonate, which is sodium and bicarbonate ion, plus acetic acid. So acetic acid has the following structure. And it causes a chemical reaction. So first, typically we would write like a double displacement reaction. So in this case, the hydrogen on the acetic acid kind of swaps places with the sodium ion. So we're left with the following. But the carbonic acid is considered unstable, so it will actually break down further into water and carbon dioxide. So let me write it down. So again, the carbonic acid will break down further into water plus carbon dioxide. So therefore, the end products of the reaction that isn't water is the sodium acetate and carbon dioxide. Okay, so let's see what the junior tutor said. The neutralization reaction between an acid and a metal hydroxide produces salt and water as a product. The reactants in a neutralization reaction are acids and bases, and the resulting products are salt and water. The reaction above is an example of a neutralization reaction. Sodium bicarbonate will react with acetic acid to produce aqueous, sodium acetate, and carbonic acid. However, carbonic acid is highly unstable and will react to form water and carbon dioxide. Therefore, the resulting reaction would be the following. Yep, so that is what I got as well. So this solution is correct. I just said that the two other products formed are sodium acetate and carbon dioxide. Okay, so question number 6. What is the balanced equation for the reaction between acetic acid and sodium hydroxide? Okay, so I'll draw down the structure for acetic acid. And it reacts with sodium hydroxide. Okay, so notice that we have an acid reacting with a base. Okay, so this kind of tells us that a neutralization reaction will occur. So I'll just say, therefore, neutralization. And when you have a neutralization reaction, this forms water and a salt. Okay, so we can see that water can be formed using one of the protons in acetic acid and the OH in sodium hydroxide. So this gives us water. And the remaining salt that takes place is sodium acetate. So this is the acetate ion. And sodium is Na+. So it is sodium acetate. Okay, so now let's make sure that the equation is balanced. We have 2 carbons on our reactant side, 2 carbons on our product side. We have 2 hydrogens on both sides, 1 sodium on both sides, and 3 oxygens on both sides as well. So reaction is balanced already. And then everything reacts at a 1-to-1 ratio. Okay, so let's see what the junior tutor said. The balanced chemical equation between acetic acid and sodium hydroxide is C3 CH3COOH plus NaOH makes CH3COONA plus H2O. Neutralization reaction between the weak acid and strong base will produce sodium acetate, which is a basic salt, and water. Since the ratio of each element on the reactant and product side from the above reaction are equal, we can say that this is a balanced chemical equation. Okay, so this solution is correct. Okay, so question 7 asks, how do you calculate concentration from absorbance? So we can calculate concentration from absorbance by using the Beer-Lambert law. So the Beer-Lambert law is the following, where absorbance is equal to the molar absorptivity times B times concentration. I'll just kind of write down what everything stands for. A is absorbance, which is unitless. And this E, which I think is the epsilon, is molar. Can also be known as the molar extinction coefficient. So this will usually be given in a question, or you need to solve for it if you're given all the other variables. And B is the path length, which is usually given in centimeters. And then lastly, C is concentration, in moles per liter. Okay, so this is the Beer-Lambert law. So typically you might be given a graph of absorbance and concentration. And when you have a line on the graph, you'll notice that as concentration increases, then absorbance also increases. So the two are related in that sense. And when you have the equation of the line, we know that absorbance is Ry. The slope is K, so which is just the molar extinction coefficient and the path length. And C is our X value. So you might be given different absorbance values depending on the concentration, and you might have to like plot them in a graph. And then using either Excel or Sigma plot, or even just knowing that the slope is equal to like rise over run. So if you remember the grade 10 math, then you can find like the slope of the line, and then you can calculate concentration from absorbance just by subbing it into your equation of the line, which would be this. So let's see what the junior tutor said. The absorbance is related to the concentration by Beer's law, which is given by A is equal to EL times C. E is the molar extinction coefficient. So you can also use L as the path length, but other sources use B. And C is the concentration. Okay, so this solution is correct. Okay, so question 8. What is the Kb value of C2H3O2 minus? The Ka value is 1.8 times 10 to the negative 5. Okay, so Kb is the base dissociation constant. And this pretty much tells us the strength of the base. So if you have a greater Kb value, then you have a stronger base. Similarly, we can have the Ka value, which is the acid dissociation constant. So when we have a larger Ka value, this tells us that we have a stronger acid. And then let's also recall what Kw is, which is the ionization constant of water, and its value is known. Kw is equal to 1.0 times 10 to the negative 14. And there is also a helpful formula that Kw is equal to the base dissociation constant times the acid dissociation constant. So if we wanted to solve for the Kb value, it will just be Kb is equal to Kw divided by Ka. So the Kw value we know is 1.0 times 10 to the negative 14. And our Ka value is given. It is 1.8 times 10 to the negative 5. Okay, so if we divide the two, we get a Kb value of 5.56 times 10 to the negative 10. So let's see what the junior tutor said. The base dissociation constant Kb is the measure of the likelihood of the base to dissociation. In general, strong bases completely dissociate, whereas weak bases only partially dissociate. The higher the Kb value of the base, the stronger it is, and the higher the tendency for it to dissociate completely. The equilibrium constant Kw is called the dissociation constant or the ionization constant of water. Kw value of water at 25 degrees is 1.4 times 10 to the negative 4, wherein the concentration of hydronium ions and hydroxide ions are equal at 1 times 10 to the negative 7. The Kb value can also be computed using the Ka and Kw value. Okay, so they showed the relationship between all of the different variables. Solving for the Kb value given above, 1.0 times 10, I think they mean to the negative 14, divided by 1.8 times 10 to the negative 5, gives 5.56 times 10 to the negative 10. Okay, so let me just fix this typo. Yeah, so it should be 1 times 10, 1.0 times 10 to the negative 10. Or negative 14, sorry. Yep, so this solution is correct. I'll just fix typos that are shown here. And for the KB expression, okay, so on to question 9. The Ka for benzoic acid is 6.5 times 10 to the negative 5. Calculate the pH of a 0.1 molar benzoic acid solution. Okay, so I'll draw the structure of benzoic acid. You have a benzene ring with carboxylic acid attached to it. So this is C6H5COOH. And when it dissociates into ions, it is deprotonated. So we get C6H5COO minus plus a proton. Okay, so next we need to construct an ice table. So ice is the initial, the change, and then at equilibrium. So we start off with a 0.1 molar solution of benzoic acid. So the initial concentration of the benzoic acid solution is the 0.1. So I'm going to put 0.1 under its initial column, or the initial row. And then for the concentration of our products, at the start of the reaction, we start off with no product, so their initial concentrations are 0. And then for the change, the reactant changes by minus X, and both of the products change by plus X. So at equilibrium, for benzoic acid, its concentration is equal to 0.1 minus X. And for both of our products, their concentrations will be equal to X at equilibrium. Okay, so they give us the Ka value, which is equal to 6.5 times 10 to the negative 5. And the Ka value can also be expressed in terms of the concentrations. So it is the concentration of our products, which is the deprotonated benzoic acid, times the concentration of protons in solution, divided by the concentration of our reactant, which is benzoic acid. Okay, so let me sub in the values that we know. We know Ka is equal to 6.5 times 10 to the negative 5. And at equilibrium, we know that both the concentrations of our products is equal to x. So when you multiply x times x, you get x squared. And the concentration of our reactant, 0.1 minus x at equilibrium. So now we just need to solve for x. So let me rewrite this equation as a quadratic formula. So we have x squared plus 6.5 times 10 to the negative 5 x plus 6.5 times 10 to the negative 5 times 0.1, which is 6.5 times 10 to the negative 4, I believe. Or negative 6, sorry. Went the wrong way. Okay, so this is our quadratic. We're left with this quadratic formula. So in order to solve for x, we can either plug it in to a quadratic equation calculator, or you can do it by hand. If you memorized it from high school, but you'll end up getting an x value. And we want to look at the positive value since we can't have a negative concentration. So x will end up being equal to 2.52 times 10 to the negative 3. So this x value is also equal to the concentration of our H+. So therefore, to solve for pH, this is equal to negative log of the concentration of our H+ ion. So we just need to sub in our value for x, which was 2.52 times 10 to the negative 3. So you should get a pH equal to 2.6. This is very acidic. Okay, so let's see what the junior tutor said. The dissociation of benzoic acid is given by C6H5COOH, which produces C6H5COO- plus H+. Hence, the pH can be calculated using the equation pH is equal to negative log of the concentration of H+. Concentration of the H+ ions needed to calculate the pH can be determined from the expression for the equilibrium constant, which is given by Ka is equal to the following. To determine the concentrations at equilibrium, we will construct an ice table as follows. Okay, so they show their ice table, the initial, the change, and the equilibrium. Substituting 6.5 times 10 to the negative 5 for Ka and the equilibrium values from the ice table, they got the following. And then they have their quadratic formula and ended up with x is equal to 2.52 times 10 to the negative 3, which is equal to the concentration of our H+ ions. Substituting this into the equation for pH, we get 2.6. Okay, so this solution is correct. I think we have time for one more question. Question 10. What are the Lewis formulas for the following molecules? So first we have a bromine attached with fluorine. If we were to calculate their total valence electrons, bromine has 7 and fluorine also has 7. So we have a total of 14 valence electrons. So let's draw a single bond between the bromine and the fluorine. So each bond contains 2 electrons. So now I just need to draw in 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that is our Lewis structure for the first molecule. Next, we have phosphorus tribromide. So its total valence electrons is equal to phosphorus having 5. And again, bromine has 7, but since there are 3 atoms of bromine, it's 21. So 21 plus 5 is equal to 26 valence electrons. So I'm going to draw phosphorus as our central atom, and then I'm going to draw the 3 bromine atoms around it. Again, each bond is worth 2 electrons, so we have 6 drawn so far, and I need to have 20 more. So each bromine atom will have 6 lone pairs, or 3 lone pairs, but 6 in total, so let me draw that in. And then if we count out all the electrons that I drew so far, each bromine has 6, so 6 times 3 is 18. And then counting all the bonds, 19, 20, 21, 22, 23, 24. So I have 24 electrons written down. So the last 2 will go on our phosphorus, 25, 26. And everything follows the octet rule, and we have our total number of electrons. So that is the Lewis structure for phosphorus tribromide. And now let's look at the last molecule, NOF. For the total valence electrons, nitrogen has 5, oxygen has 6, and fluorine has 7. So if we were to add them all together, we have 18 valence electrons in total. So our central atom here would be nitrogen. And first I'm just going to write it as a single bond with both the fluorine and the oxygen. And then if we were to fill in all of the lone pairs, fluorine has 6. So it already has a full octet. So I know I don't need to form a double bond with the fluorine. But if I were to draw in all of the lone pairs on the oxygen, there would be 4. And nitrogen still doesn't have a full octet, so that's why I've joined a double bond in between the oxygen and the nitrogen. But we still don't have a full octet for the nitrogen, so I'm going to add another lone pair. So now let's count it out to see if we have 18. So we have 4, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18. So that is the Lewis structure for NOF. And the junior tutor said, The bromine and the fluorine would just have a single bond. The phosphorus tribromide has the 3 bromines and then a lone pair on phosphorus. And the NOF has the double bond between the oxygen and the nitrogen and a lone pair on the nitrogen. Okay, so this solution is correct. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can leave it a thumbs up and a comment. And don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.